to just give you an example now, and further details of scaling will come in lectures in your studies. Imagine that you are asked to build a new dome in Aachen, which is 500 meters high, enormous Aachen dome. And you are asked to make that out of the Maastricht limestone. Okay, you say, that's very nice. Give me the drawing, and they give you the drawing of this beautiful new Aachener dome. I'm going to make a small model. So the 500 meter I reduce to 1.5 meter. Therefore, I take the Maastricht limestone, I make very small blocks out of it, I pile them on top of each other, I make my model, and look, it stands up. It's beautiful, maybe I shake it even a little bit, it stands up. And therefore you conclude the dome which I'm going to build for a lot of money, 500 meters high, is going to be stable. Okay? Now this argumentation is wrong. And most of you probably know why it is wrong. Because if you reduce the size of the model, then the stresses, which are trying to break the little stones, are also reduced. There is a very, very important formula. We are going to see it many times in this lecture. The stress is the density the acceleration of the gravity times the height. I'm not going to explain it now, but just start to keep this in mind. I will explain the formula later on in the course. If you reduce the height, you reduce the stress. Therefore, the stress in this model church is much smaller than it is in reality. But the limestone is the same. Okay? So now you are trying to see if the church is stable by putting a much, much lower stress on the limestone than it is going to really feel when the church is built. So the way to scale your experiment is to reduce the strength of your model material by the same amount. So maybe you would have to build your model church out of something which is rather soft, like these cookies. It's very important in these scaled experiments to know how the equations for scaling work. And it's very important to make sure that the scaling ratios are correct. But then you can really do amazing things. This model, which was published in a very high quality international journal, really reproduces many, many of the aspects that are present in grabens that you can see in Iceland, or in Djibouti, for example, or if you go down in a submarine to see the mid-oceanic ridges. Scaled experiments. Scaled experiments are actually quite old, and they are a part of the toolbox of engineers in many different fields. For example, wind tunnels. If engineers want to build a new airplane, they don't want to build it to the real size. They test a small model in a wind tunnel. Why do you do that? Why do you use a wind tunnel? It is simply because there is no computer available at the moment that can calculate everything that you want to know. The results are just too complicated. The same holds for these models. The complexity, which I've shown you in these models, there is no computational method at the moment which allows you to really calculate these kind of models. One of our research groups in Aachen here works with the supercomputer which we have here in Aachen, and we can make very, very small and very primitive versions of these models. And they take an enormous amount of computing time. But these scaled models are, of course, not very difficult to make in principle, and some of them are quite old. This one is very famous, made by Close in Bonn in 1935. It was included in his famous paper, Experimental Tectonic. I would really recommend that you check out this classic paper. It is now online. The mathematics and the physics is not there yet, but this guy had a fantastic intuition of how we should make these models. And here is his model of a ground. It contains not just one big fault, but it contains many small faults. And in fact, if you look at the Rheingraben, for example, the boundary of the Rheingraben, it looks just like this. Okay, so he had a very good intuitive feeling of what he should do. It was not very quantitative, but groundbreaking work, 1935. These scaled analog models, if you want, are nowadays a kind of an art. There are laboratories, we have one here in Aachen, that have a lot of techniques to mimic what is going on in the Earth. For example, this model here is what is called a growth fault. A growth fault is a fault that moves during sedimentation. If you drive your car from Aachen to Bonn, or from Aachen to Köln, you are going across many growth faults. The land is sinking, and in the parts which are a little bit deeper, that's where the rivers are going, so there is more sediment accumulated in one half of the fault than on the other half. And therefore, the red layers here are much thicker than here. And we have a PhD student or a really experienced Hiwi who is actually sprinkling the sand, depositing on one side, which is going down to make sure that the land surface is kept at the same level. Other experiments, people have water running through the experiments. They can mimic the sedimentation processes, or you can use some kind of a device to remove material and model the erosion. So these models are very nice because you can really touch them, you can work with them if you like these kind of experiments, and they have a huge potential to understand processes in tectonics and structural geology. But of course it's very difficult to measure all the stresses in these models. Okay? So what nowadays is done more and more is that these models are combined with numerical models, computer models. And here is one example that we have calculated here of a kind of a similar experiment. Okay, maybe I go back here. You can see that there is this basement here that has gone down, and on this side there is more sediment, and here is a fault which was formed in the sand. Okay? Now this is a computer model of more or less similar materials, similar movements. Here the basement is going down, and this here is now a calculated contour of the amount of deformation. Of course, if you have a fault, then there is a lot of deformation in the fault. So this is where the material has gone down. You can see that there is another one here. Everything is very exact, but there is still almost no computing method which is capable to reproduce all the details of the fine details of these analog experiments. So the two of these are nowadays combined more and more, used to test each other, used to calibrate each other, and I think that the coming 5 years, the coming 10 years, both of these methods, the physical models and the numerical models, are going to be very important. And now I'm going to hopefully show you, another model done by a colleague in New Zealand. And this model is a numerical model of the formation of the Alps. It runs over maybe 35, 40 million years, and it shows you one continent with little rifted blocks on it, which is being subducted under the other continent, 1 centimeter per year. That is the motion of the plates. And now So what is very important is that in these models you have really to define the material properties. There are a huge list of numbers that you have to put in, but then once you've done that, then you can start running it. And the way it is being done, this is a so-called finite element model, is that the whole Earth is broken down into small blocks, into small numerical cells, like this one here. And each of these cells has the properties, and the model has some kind of a boundary condition, like movement of the subducting plate. And then in small time increments, the computer tries to find a solution so that there is mechanical equilibrium, so that nothing flies away or there are no holes in the model. And these solutions are then computed over the next time step, and the deformation is shown by the original grid lines. Okay, so here the model has already deformed a little bit, and now you can follow it. This is the first continental block that goes into the subduction zone. Here is the second continental block which is coming. You can already see the mountain belt which is formed here. Here's the second block, goes down into the subduction zone. And then after the end of the subduction phase, you get the continental collision. The two continents start to collide. And this continent doesn't want to go down into the subduction zone. It's far too light. So what it does, it starts to push up the second half of the mountain belt, and you generate this huge whirlpool of very, very strongly deformed rocks, which is now the Alps. Okay. Later on in the study, you are going to see many more examples of such models. Okay. So far, so good. But to be able to become a structural geologist that is able to work with geometric models, with kinematic models, with dynamic models, you have to learn a lot of things. And the first thing that the structural geologist has to understand is vectors, because vectors are the basic building block of any structure. If you want to describe a geometry, then you have to understand vectors. So, very, very simple. This is really secondary school stuff. I have to define my coordinates, x1 and x2, and my vector f here is defined by these 2 points. There's an angle that you can put here, and of course the length of the vector is, according to the Pythagoras rule, the square of this one plus the square of this one, and the root of that. And the f1, the one component of the f, is the length divided by the cosine, and the second is the sine. A very important thing, that components of this vector in a different coordinate system. So now I change the coordinate, the vector is the same, and now my x1 axis is like this, and the x1 axis is like that. And the challenge or the question is, how do I compute the coordinates, these ones here, f1 dot and f2 dot, in a new coordinate system? That's quite simple. The f1 dot is the f1 times the cosines. Okay, f1 is here, times the cosine of the wing of the angle of rotation between the two coordinate systems, plus the f2 times the sinus of the rotation. And the other one, f2 dash, is minus